All right, now that we have built our Lewis dot structures of our atoms, now we are asking ourselves, what do we call these different shapes? What determines the shape of our molecule? So one of the things that we need to realize that each and every one of our atoms in the center has a nucleus, right? So in that nucleus is our protons and our neutrons. And what surrounds our atoms? Well, it's our electrons. So there are these unpaired electrons and electrons all around our atoms, and those electrons play a large role in determining the three-dimensional shape. And we're talking more sphere shape, okay, than a circle. All right, so this is two-dimensional, this is three-dimensional with all kinds of shading that I can't do on here. All right, and if everything has these negatively charged electrons, what do one electron do to another electron? They repel. They want to stay as far apart from one another as possible. So that's what we have to keep in our minds, is that there is this valence-shell electron pair repulsion theory, or called VSEPR for short. Okay, and that is the tendency of these electron pairs to change how they are positioned so that they maximize the distance between them. They are repulsed by one another. Okay? So we're going to look at two things when figuring out what the VSEPR shape is going to be. We're going to look at the bond angle, and there are 3 points that define an angle, A, B, C, okay, where B is going to be our central atom, and the A and C are going to be the things bonded to it. And we're going to look at this thing that doesn't appear in your textbook but is important to know, your steric number. The steric number is the number of substances around the central atom. So that means atoms bonded to it and lone pairs, because they both count. So I cannot have you guys star circle highlight that anymore, all right? Make sure that you pay really close attention to that point, and I'll show you why. All right, so a bond angle is exactly what it looks like, okay? So you have your central atom here. This is for ammonia, NH3. All right, so this is your nitrogen. Here is one of your hydrogens. Here's another of your hydrogens. Here's another of your hydrogens. And the bond angle looks like so. And I believe for ammonia, it's 107.8 degrees. And nitrogen has 2 lone pairs up here. These lone pairs that appear right here actually repel the electrons that are right here on all of the hydrogens. And when it pushes them down, it gives that specific bond angle. Okay, so this chart right here is all about our VSEPR geometries. All right, and it's a nice little way to put these all into perspective with one another. Okay, so here's the chart. It has your steric number, which again is the number of atoms and lone pairs together. And then it has going across the number of lone pairs that we actually have. Okay, you're going to be responsible for a steric number of 2 and a steric number of 4. We don't have to worry about 3, 5, or 6. So we're really only worried about 4 things. Okay, so a steric number of 2 means that you have your central atom. E is your central atom, or the atom in the center of everything. And X are the atoms bonded to it. Okay, bonded atoms. So how far can 2 things really get from one another? On complete opposite sides, right? So that's 180 degrees. And we call that shape linear, meaning one full line. Okay? Now, if we have a central atom and 4 things bonded to it, the maximum bond angle that it can get is actually 109.5 degrees. And here's that word tetra again, tetrahedral shape. A lot of people think that it would be a T, which would be 90 degrees, all right? A T shape is only two-dimensional. What you don't realize is if you have your central atom in the middle and you have something above it, you can have something coming out to the side, something coming out in front, and something going away from you. And that maximizes the bond angle to 109.5 degrees. And 109.5 is greater than 90 degrees. And if you are being repulsed by something, repelled by something, you're going to want the bigger bond angle. Okay? Now, if one of the things around the central atom, okay, you have your three things bonded to it, but one of them is a lone pair, this has like more electrons than a regular element would. So it's going to be extra repelly. So when that happens, you have a bond angle of 109.5 degrees or a little bit less. And it is called a trigonal pyramid or a triangle-based pyramid. So it basically takes this part where you are coming towards you and away from you, and it draws this little triangle. Oh, come on, change my color. It draws this little triangle underneath, and I'll show you some pictures of that. These electron lone pairs up here push the bond angle down. Okay, so trigonal pyramid is a triangle-based pyramid. And if we have two things bonded to the central atom, but the steric number is 4 because we have two lone pairs, these two things literally start pushing down on it even more. And you get a bent or angular shape. Most people just say bent. So again, if you have this right here, you have something here and something coming out towards it, and then you have a lone pair here and a lone pair here that would be pushing down. Okay, and we'll talk about what water and everything looks like as well. All right, so some examples of this. All right, so for two things around our central atom, a steric number of 2, okay, is going to give you a linear shape with a bond angle of 180 degrees if there is no lone pairs. So this would be your Be and Cl and Cl, and they would make a complete straight line. Okay, carbon dioxide is also going to have a linear shape. It doesn't matter if it's a single bond or a double bond or a triple bond. Hydrogen cyanide, which actually has one single bond and one triple bond. You count the number of atoms bonded to it, not how many different types of bonds there are between. But it's basically going to repel and be in a nice straight line from one another. Okay? The steric number of 4, okay, is going to have a tetrahedral shape, and that's a bond angle of 109.5 degrees. You'll see this little wedge means coming towards you, and this little dash means going away from you to show that it is actually three-dimensional. And as long as you have no lone pairs, it takes this nice tetrahedral shape. So methane, CH4, is going to have that. Dichloromethane as well, silicon, tetrachloride, phosphorus with an oxygen and 3 chlorines, they're all going to do the same thing. Those 4 things can be as far away from one another as possible at a 109.5 degree angle. If you have 4 things around the central atom, but one of them is a lone pair, that's where you get that triangle-based pyramid. All right, and that is your nitrogen trihydride or ammonia, phosphorus trifluoride, and then you have your ammonia right here. So you end up having your nitrogen with a lone pair. It has a hydrogen bonded to it, another hydrogen bonded to it, and your chlorine atom around it, making that bent shape come down and make that triangle-based pyramid. If 2 things are lone pairs, when 2 things are bonded to it for a steric number of 4, it will be that bent or angular shape. All right, and this is where we get into water shape. Okay, it has 4 things around the central atom, steric number of 4. So that means that this is a 1, a 2, a 3, and a 4. Steric number of 4. That will bend my bond angle down to less than 104.5. Okay, so specifically for water, since this is a molecule that we're going to spend a lot of time with, it has a very specific bond angle of 104.5 degrees. So you definitely want to remember that because the 2 lone pairs on oxygen are going to make it so that it bends down. It is not linear. The 2 things that are attached to the oxygen don't go in a straight line. Okay, if you put the 2 lone pairs like this, it's technically drawn correctly, but you are going to be more likely to say, oh, this is linear, when it's actually not. This would be like a Google Earth image, okay, whereas this is a Google Street View. And I'll show you what I mean shortly. Okay, so this is still bent. So you always want to draw your lone pairs next to one another for anybody in column 16 like oxygen and sulfur because you want to kind of set yourself up for that bond angle. Okay, so here we have these different PhET simulators. I'm going to show you the molecule shapes one and that'll kind of clarify everything for you. All right, so when you're here, you're going to click on your molecular geometry and your electron geometry, and we're going to show our bond angles. So this is 2 things around our central atom, like so. Okay, so here you see you are at 180 degrees. It doesn't matter how you push it, they're always going to repel one another. If you just have 2 things bonded to one another, it's still called linear, even though we don't technically have a bond angle. But here are 2 things bonded to one another. Now, if we put in 4 things, you'll see this is that tetrahedral shape. Okay, so this tetrahedral shape is going to have 4 things around our central atom as maximized as possible. And you'll see that there's 1 thing going away from you, towards you, and 3 points to find a plane, like so. If we get rid of one of the bonded things and put in a lone pair, you'll see that it completely changes your bond angle. Okay? If you didn't have the lone pair, they would all be in the same plane. But when you do have the lone pair, it repels these pairs down and changes it from a planar to a pyramid. So watch that again. Planar becomes pyramid. Now if I get rid of one of these other bonds and add another lone pair, notice it is not linear. Okay, it is bent. All right, so when I was telling you that Google Earth street image and stuff like that, here is your water molecule. Okay, it looks linear, but it's not. All right, so if we get rid of these bond angle or these lone pairs, you'll see the bond angle changes to 180. But when you add them, it changes it to that 109.5. Now we can go to the real molecules and quickly see some of those as well. So here is our water, all right, with that 104.5 bond angle here. Here is our image that looks like it is linear, but it is most definitely not. It is bent like so. And then you can do your carbon dioxide and see your linear 180 here. You can see your methane, your CH4, and you can see how we are at 109.5 degrees. You can have NH3, which is your 107.8 degrees with your trigonal pyramid. And then we have our the bent shape with our water. All right, so that is the intro to VSEPR geometries.